Good morning. Last class we discussed about instrumentation amplifier. In that we discussed about introduction and good requirements and analysis as well as advantages. Now we are going to discuss about applications of instrumentation amplifier. In this applications of instrumentation amplifier, mainly we are having four types of applications. One is temperature controller, and the second one is temperature indicator, third one is light intensity meter, and the fourth one is analog weight scale. These are the four applications. In these applications we are using the instrumentation amplifier. Okay, so now I am going to using a Wien bridge along with the instrumentation amplifier, okay, for temperature controller, as well as the same circuit I may be used for the temperature indicator also, and I may replace the thermistor with the help of photocells for the calculation of light intensity. I may use the circuit for the light intensity meter also if you replaced thermistor by photocells. So with the same circuit we can explain three applications of instrumentation amplifier. First, coming to the temperature controller. So in this circuit we all know that this is nothing but the 3 op amp combination is nothing but the instrumentation amplifier, and you are very well known about why we are using these instrumentation amplifiers. To amplify the low level signals we are going to be used as instrumentation amplifiers. Now here coming to in this case the thermistor is placed at one of the arms of transducer bridge. Here it is the transducer bridge. Why I am considering it as the transducer bridge is the output of the transducers are very low. So the outputs of the transducers are amplifying with the help of instrumentation amplifier. That's why I am considering it as a transducer bridge. Okay, one of the arm we are placing the thermistor on one of the arms of the transducer bridge. Now at a particular reference temperature the bridge is balanced. That means VA will be equal to VB, and also we can express the bridge is balanced by this valid condition. RC by RA will be equal to RB divided by RT. This is also take as a reference of the bridge balanced condition. Now what I am telling is at a particular reference temperature the bridge is balanced. In that reference temperature the output voltage is 0. We all know that the output voltage of the instrumentation amplifier V0 will be equal to R2 divided by R1. V0 will be equal to R2 divided by R1 into VA, and here we are treating it as VB. Now VB minus VA. From this circuit we are considering the output voltage of the total temperature controller is V0 is equal to R2 divided by R1 into VB minus VA. Once the bridge is balanced, then VA will be equal to VB and we will be represented V0 is equal to 0. Now when the temperature is falling on the thermistor, then automatically the resistance value will be changes. Once the resistance value is changed, then what happened to the output voltage? The output voltage is also changed. Why? Because here once the resistance value is changed, the bridge is unbalanced. So automatically the output voltage is also getting other than 0. So that output voltage will drive the relay and heating circuits, and these relay and heating circuits are act as a switch to control the temperatures of the thermistors. Like this, we are going to be used the instrumentation amplifier as a temperature controller. I think now you can clearly understand about the application of one of the application of instrumentation amplifier. Now what I am going to tell you is the same circuit will be used for the temperature indicator also. Okay, if you are adding a temperature indicator at the output of the instrumentation amplifier circuit, first we are going to find out the bridge balancer condition. At a particular reference temperature, the bridge is balanced. In that condition, V0 is equal to 0, and this meter is calibrated for the calculation of the reference temperatures. So we will note that reference temperature with the help of this meter. Okay, temperature indicator meter. Next, if the light is falling on the thermistor, then the resistance value will be changes. Once the value is changes, then the bridge is unbalanced and we will get some output voltage. And again we are getting the temperature range, temperature variation in the temperature indicator meter. So with this temperature indicator meter, we can clearly identify the range of temperatures for getting the bridge is balanced as well as for the bridge is unbalanced. With this temperature indicator, we are going to design the accurate gain of the instrumentation amplifiers. Next, coming to the light intensity meter, replace thermistor by photocells. Then in the darkness condition, the bridge is balanced. In that case, we will be connected the light intensity meter at the output of the instrumentation amplifier, and in the darkness condition, the output as 0. Okay, that will be noted in the light intensity meter. Once the photons or the light is injected on the photocells, then what happened? The resistance value will be changes. Then automatically the output bridge is unbalanced and the output voltage is changed, and there is a deflection in the light intensity meter also, and that light intensity meter is used for the calibrating of the flux. Okay, for the measuring of the light. With this, we can calculate the accurate light intensity value. Okay, with this same circuit, we calculated all these three applications of instrumentation amplifier. So the instrumentation amplifier will be used as a temperature controller. With the help of instrumentation amplifier, we can on and off of the temperature controller, and with the help of temperature indicator, we can connect at the output, we can connect the temperature indicator device. With the help of that, we can calculate the ranges of temperature, and with the help of light intensity meter, okay, now we can measure the change in the flux, light change in the flux density in the light intensity of the flux will be easily calculated with the help of the same instrumentation amplifier. Next, we are going to discuss about the analog weight scale. For that, I am going to draw the circuit for the analog weight scale. Now I am going to explain last application of instrumentation amplifier, which is nothing but analog weight scale. Coming to in this application, the Wien bridge, same bridge will be used along with the instrumentation amplifier. But in the previous cases, we have used the thermistors as well as photocells on one of the arms of the bridge. But in this case, what I am going to use is I am placing analog weights on all the four arms of the bridge. That's why we are treating it as a analog weight scale. Okay, now what I am going to do is if there is no element placed on the base of the weight platform, then the bridge will be balanced. So automatically we will get the output voltage as 0. So if there is any element placed on the base platform of the weight, then what happened is opposite arms, one of the opposite arms are elongate and the other opposite arms of the bridge are compressed. So elongate means it will be increases and compressed means it will be decreases. So here I am considering RT1 and RT3 resistance will be decreases when the weight is placed on the platform. Okay, and RT2 and RT4 weights are increased when we are placing the weight on the bridge. So I am going to calculate VA and VB. So once we place the weight on the base of the weight platforms, automatically the bridge is unbalanced. Now first I am going to calculate VA value by using voltage divider rule. VA will be equal to VDC into R minus delta R. Here I am treating it as RT1. R minus delta R divided by R minus delta R plus RT2 means R plus delta R. Why? Because when you are placing the element on the base of the weight platform, then RT1 and RT3 will be decreases and RT2 and RT4 opposite arm will be increases. So according to the voltage divider rule, VA will be equal to VDC into RT1 by RT2 plus RT1. That's why VA is equal to VDC. RT1 will becomes R minus delta R. RT2 will becomes R plus delta R. So you will get it as VDC into R minus delta R divided by 2R. Similarly, calculate the value of VB. Same using voltage divider rule. Now in this case, VDC into RT4. RT4 means if you are placing the element on the base of the weight platform, then RT4 and RT2 will be increases. Then RT4 will be R plus delta R divided by R plus delta R plus RT3 means R minus delta R. So in this case, we will get VDC into R plus delta R divided by 2R. So finally we are applying the VA values and VB values at the basis of two non-inverting terminals. From there we will be calculated the output voltages of the instrumentation amplifier. So V0 will be equal to gain into VB minus VA. If we have taken VB minus VA and take common as VDC by 2R, VB minus VA, and from this substitute VB value and VA value and then take VDC by 2R as common. A is gain and VDC by 2R if you have taken as common, then it will becomes R plus delta R and then minus R plus delta R. Then what you will get is A into VDC divided by 2R into 2 into delta R. So 2 will be cancelled. We will get VDC into delta R divided by R into A, which is nothing but the output voltage. When you are placing an element on the analog weights Okay, this is about the output voltage of the instrumentation amplifier. So always the output voltage of the instrumentation amplifier, if we are including the analog weight scale circuit, then what happened is the output voltage is always depends upon the change in the output voltage is always depends upon the change in the resistances value. If the value of the resistance is changes, then the output voltage is changes. If the value of the resistance is 0, change in the resistance value is 0, then the output voltage is 0. If you think output voltage is 0, the bridge is balanced. That indicates we are not placing any element on the base of weight platform. This is about analog weight scale. So all these 4 applications are regarding to the applications of instrumentation amplifier. So whenever they are asking you to write about the instrumentation amplifier in detail, then you have to write about the analysis, good requirements of the instrumentation amplifier, along with you have to write the advantages and also the applications of instrumentation amplifier. Now we are going to discuss about AC amplifiers. First, before going to discuss about different types of AC amplifiers, first of all, we have to know about what is an AC amplifier. Op-amps are responding to both AC signals as well as DC signals also. That's why we are calling op-amp as a versatile device. If the op-amp responds to the AC signals, then we will be called it as AC amplifiers. For these AC amplifiers, we have to take care of low and high frequency limits. Very important thing in the AC amplifier. And sometimes the DC level is also produced along with the AC signals. In that type of AC amplifiers, we are going to be used the coupling capacitors. Why we are going to be used those coupling capacitors is to block the amplification of DC levels. In that cases, we are going to be used that coupling capacitors. For an example, if I am considering an audio system which consists of several number of stages, it is possible to produce the DC level at the output of audio systems. So if you are considering that DC level also along with the AC signals, then automatically we will get the distorted output at the output side. For that, what we have to do is we have to restrict that DC level, or you have to eliminate that DC level. So we are going to be used the coupling capacitors to block that DC level. Generally capacitors block DC and allows AC signals. That's why in those case of AC amplifiers, we are going to be used the coupling capacitors. And the main types of AC amplifiers are, we are having 2 types of AC amplifiers. One is inverting AC amplifier and the other one is non-inverting AC amplifier. First we are going to discuss about inverting AC amplifier. Okay, coming to say this, why I am calling it as inverting. I think you are all very well known about why I am calling the op-amp as an inverting op-amp and why we are calling an op-amp as a non-inverting op-amp. In this case, we are applying the input at the inverting terminal of an op-amp. That's why I am treating it as a AC amplifier. And to get the accurate output at the output side, we have to nullify the offset errors. For that, we are going to be used used the compensation resistors. Along with we are going to use the compensation network. Those are used to eliminate the errors. So because of eliminating the errors, we will get the accurate output at the output side. If we are not eliminating those errors, because of those offset errors, we may not get the accurate outputs. That's why here we are using our compensation resistance as well as compensation network to nullify those offset errors. And these offset errors are generated because of mismatching of the components and thermal drift and tolerances. So these will be eliminated with the help of our compensation and compensating network. Now I am going to calculate gain of the AC amplifier. First I am going to take the input side. Okay, so what happened is I want to calculate the potential at A. Once we calculate the potential at A, then it is easily to write the output voltage of inverting amplifier, that is V0 is equal to minus RF by R1 into VA. So first we are concentrating on calculation of potential at node A. For that I am considering the input block as here it is RS and it is V in, and here we are using the coupling capacitors CC, and here I am taking it as X node, and here input resistance with feedback and at A, and according to the virtual ground concept, if B is connected to ground, obviously, so the potential at B is at ground, obviously the potential of A is also at ground. So both here V in other end of the input is also connected to ground. Okay, now I am going to calculate Vx. Okay, so what happened for Vx? We can easily calculate Vx value by using this circuit Vx by using voltage divider rule. Vx is equal to V in into RIF divided by RS plus 1 by J omega Cc plus input resistance with feedback. Okay, so solve that value Vx, then it is both are at the same potential, so Va will be equal to Vx, then we can directly write V0 is equal to minus Rf by R1 into Vin. So now I am going to solve that equation, so we will get it as Vx will be equal to Vin into Rif divided by Rs plus Rif into J omega Cc plus 1. V in into RIF divided by RS plus RIF into J omega Cc plus 1 into J omega Cc. We all know that omega is equal to 2 pi f. Now substitute omega is equal to 2 pi f in this equation. Then you will get V in into RIF into 2 pi f into J into Cc divided by Rs plus RIF into J 2 pi f Cc plus 1. We are assuming FL is equal to, why? Because for the AC amplifiers we have to take care of lower frequency level as well as higher frequency level. Here I am taking FL is equal to 1 divided by Rs plus RIF into 2 pi Cc. So substitute this value in this equation, then you will get Vx is equal to J into V in RIF into 2 pi f Cc divided by J into F by FL plus 1. Okay, that is about Vx value. Once we know the value of Vx, both are at the same potential, Vx and Va. So the potential at A will be treated as the potential at X. Then we can directly write the output voltage. V naught will be equal to minus of Rf divided by R1 into Va, which is nothing but Vx in this case. So it will becomes minus Rf by R1 into Vx. So we can easily calculate this value by placing that value Rf divided by R1 into J into Vin into RIF 2 pi F Cc divided by J into F by FL plus 1. Okay, so that is nothing but V naught value. Once we calculated the V naught value, so we can easily calculate the gain also. Once we know the value of V naught, then we can easily calculate the gain value, which is nothing but V naught divided by V in will be equal to minus of Rf by R1 into J RIF into 2 pi F Cc divided by J into F by FL plus 1, which is nothing but the gain. V naught by V in is equal to minus Rf by R1 into J into 2 pi F RIF into Cc by J into F by FL plus 1. When the frequency is increases, what happened for the gain? This frequency is directly proportional to gain. So if you are increasing the frequency, the gain is also increases until at F is equal to FL. What happened at F is equal to FL? The denominator will becomes, when F is equal to FL, the denominator will becomes 1 by J into 1. So it will be calculated as 1 by root 2. So 20 log of 1 by root 2, that will be equal to minus 3.01 dB. It will shows the overall effect on the gain. So this minus 3.01 dB will be taken as what we are considering that as. That will be taken as break frequency or corner frequency. So FL will be taken as lower cutoff frequency. Why I am taking that FL is lower cutoff frequency? At F is equal to FL, what happened is the denominator will becomes root 2, 1 by 1 plus J 1. Then if you calculate the gain, then the 20 log of 1 by root 2 is equal to minus 3.01 dB. That's why we are treating it as a corner frequency or break frequency. If you are representing the frequency response, here I am taking as frequency and here I am considered as a gain. As you increase the frequency, the gain is also increases until the frequency FL. Once it reaches the FL, okay, then if you increase the frequency greater than FL, the gain will be flat, and it will be flat until the higher cutoff frequency. Once it reaches the higher cutoff frequency, again the gain will be changes. So we require lower cutoff frequency limit as well as higher cutoff frequency limit for the AC amplifiers. So the higher cutoff frequency is depends on the closed loop gain of AC amplifier. So finally the bandwidth of the AC amplifier will be taken as FH minus FL. Okay, and the coupling capacitor CC will blocks the DC component present in the circuit at the input side of the circuit. So this is regarding to the AC amplifier. Coming to the non-inverting AC amplifier. Just now we have seen it the inverting AC amplifier. The AC amplifier means the op amp is responding to the AC signals. That's why we are calling it as AC amplifier. And what is the difference between non-inverting AC amplifier as well as inverting AC amplifier? We are applying the input at the inverting input terminals of an op amp in case of inverting AC amplifier. Now for the non-inverting AC amplifier, we are applying the input at the non-inverting terminal of the AC amplifier. Okay, now here we are using the compensation resistors as well as the compensation network. Why I am using these compensation resistors and compensation networks is to bypass the offset errors for getting the accurate output at the output side. For that I am going to bypass the offset errors, so I am using the compensating resistor or compensation, which is nothing but R1 parallel RF, and that I am using the offset compensation network. So if you are observing the input circuit, it should be looks like the circuit of the inverting AC amplifier. Here I am going to represent that input circuit. See this one. Here we are having resistance, source resistance RS, and here we are applying the input as V in and connected to ground, and here we are connecting the capacitor CC. Okay, here it is B, and here we are connecting RIF, and directly it will be connected to ground. So I am connecting like this. If you observe this circuit, it should be same as it is that of what we have used for the inverting AC amplifier. From there only we calculated the VA value. So similarly in this case we are going to calculate the VB value. And why I think you all very well known about why I am including the capacitance. Why? Because to block the DC levels to present in that circuit. That's why we are using that coupling capacitors. While you are going to design the AC amplifiers, you have to take care of lower frequency as well as upper frequency limit. Now I am going to calculate the value of VB. Once I calculate the value of VB, the output voltage of the non-inverting amplifier is 1 plus RF by R1 into VB. So first I am going to calculate VB. VB is nothing but use voltage divider rule. Then it will becomes V in into RIF divided by RS plus 1 by J omega CC plus RIF. If you observe this, the equation is also same as it is that of what we get in the previous case. Now solve this one and calculate the value of VB. Now I am going to write directly, so which is nothing but 2 pi F CC into V in RIF divided by RS plus RIF into J into omega CC plus RI plus 1 plus 1. Now what happened is VB will be written as VB is equal to what? How can we represent the VB value? VB is equal to J into 2 pi F CC into V in RIF input resistance with feedback divided by 1 plus RS plus RIF into J into 2 pi F CC. Now I am going to calculate the VB by I am taking FL is equal to 1 by RS plus RIF into 2 pi, so CC. So we can rewrite this equation as VB is equal to J into 2 pi FCC V in into RIF divided by 1 plus J into F by F L. Now finally output voltage V0 is equal to, this is non-inverting op-amp, so we can rewrite it as 1 plus Rf by R1 into Vb. Okay, substitute Vb value in this equation, we will get V0, directly I am writing V0 by Vin will be equal to 1 plus Rf divided by R1 into J2 pi f Cc Rif divided by 1 plus J into F by Fl. So if we observe this gain equation, what can we conclude is the gain is equal to 1 plus Rf by R1 into J2 pi f Cc Rif divided by 1 plus J into F by Fl. So when the frequency is increases, what happened for the gain? Gain is also increases. But until at F is equal to Fl. Once it reaches the value of Fl, then the denominator will becomes 1 by 1 plus J into 1. That will be equal to 1 by root 2. If we have taken the 20 log of 1 by root 2, then that will becomes minus 3.01 dB, which is nothing but the break frequency or corner frequency. It shows its effect on the overall gain. So if you are going to draw the frequency response, what we have seen it for the previous case, same thing here also we are going to observe. If I am going to take the frequency response F and gain in dBs, what happened is until F is equal to Fl, the frequency will be increases. Once it reaches the Fl value, then after Fl the gain will be flat until Fh. Okay, so the Fh, higher cutoff frequency value is depends upon the closed loop gain of AC amplifier in this case. So finally bandwidth will be calculated as bandwidth will be equal to Fh minus Fl here, and non-inverting not only for the non-inverting AC amplifier, for the inverting AC amplifier also the lower cutoff frequency is controlled by the capacitance Cc value. Okay, so the gain will be equal to AF will be equal to mainly 1 plus Rf by R1. So V0 by Vin is equal to, we can represent it as AF into this value. So this is representing about non-inverting AC amplifiers. So whenever they are asking you to write about AC amplifiers, you have to write inverting AC amplifier as well as non-inverting AC amplifiers. Once you can observe the circuits, here we are using the compensating networks, whereas in case of inverting AC amplifier also we used the compensating network as well as compensating resistance. What is the use of this compensating resistor as well as compensating network in both the cases is to eliminate the offset errors. If you eliminate the offset errors, you will get the undistorted output at the output side. So to get the output voltage value is accurate, we have to eliminate these offset errors. That's it for the AC amplifiers. Today we are going to discuss about voltage to current converter. So in this case, the output load current is directly proportional to input voltage. That's why we are calling it as voltage to current converter. Depending upon the connection of load, again voltage to current converters are divided into two types. One is floating type and the other one is grounded type. First, I am going to explain about floating type load. Here, if you consider these two circuits, one is inverting op-amp and the other one is non-inverting op-amp. In both the cases, we are not connecting the load to ground. That's That's why we are calling it as a floating type. So first what I want to tell you is the current drawn at the input terminals of an op amp is 0. So the total current passing through the op amp is same. So II is equal to IL. You may consider any one of the circuit, no problem. Whether you may consider the non-inverting op amp circuit, or you may consider the non-inverting op amp circuit, no problem. So here I am considering the non-inverting op amp circuit, and the voltage potential at B is equal to and the potential at A should be calculated. So by using the virtual ground concept, the potential at A will be equal to potential at B. So now I am going to calculate first VB value. VB is equal to VA. How can we treat VB is equal to VA? According to the virtual ground concept, the potential at A will be equal to potential at B. The potential at A will be equal to VI. So automatically the potential at B is also equal to VI. So I am considering VB is equal to VI. So now according to the Ohm's law, I am going to calculate the current in between these two nodes. So what happened? I is equal to VB divided by R1. VB divided by R1, and just now only we discussed that according to virtual ground concept, VB is equal to VA. So VA by R1 which should be taken as VI divided by R1. So I is directly proportional to and we are also consider input current I will be equal to load current. So what I am considering is II is equal to IL. So if you consider IL, then that will be also equal to VI divided by R1. So if you observe the final equation, IL is equal to VI divided by R1, then IL is directly proportional to VI. So you can conclude that the output load current is directly proportional to input voltage. That's why we are calling it as voltage to current converter. And for removing that proportionality constant, always we are going to consider a constant value which is nothing but 1 by R. So this is also called as transconductance. Okay, why we are calling it as transconductance is because of this 1 by R, and we may also call it as voltage controlled current source. And whatever may be the load, the always load current is depends upon the magnitude of input voltage and resistance. It doesn't depend upon the load. If the load may be a linear load, if the load may be a resistor, or if the load may be a transistor, or if the load may be a capacitor, whatever may be the load, we don't bother about the load. Always the load current is depends upon the input voltage and resistance. So IL is equal to VI divided by R1. Suppose if you replace the load resistance RL with capacitance C, then it will take some time to charge as well as to discharge the capacitance value. So these type of circuits, if you include the capacitance in place of load resistance, then it will take some time to charge the capacitor as well as discharge the capacitor. So these type of circuits will be used in the sawtooth wave generators as well as triangular wave generators. So this is about the voltage to current converter. In that we discussed the first thing, which is nothing but the floating load. How we will be called it as a floating load is here the other end of the load is not connected to anywhere. That's why we are calling it as a floating load. That's why initially I told you that depending upon the connection of load, we are again divided the voltage to current converters into two types. One is floating load and the other one is ground load, ground type load. Next I am going to explain the ground. Now I am going to explain Voltage to current converter with grounded load. Previously, we have seen it that voltage to current converter with floating load. Once we connect the load to the ground, then it is no longer possible to place the load in the feedback loop of the op amp. Once we connected the load to the ground, very important point this one. That's why only we are calling it as the grounded load, and we are not included the load resistance in the feedback path. Why? Because once you connect the load connected to ground, it is no longer possible to place that load in the closed loop of op amp. So here I am considering the load is connected to ground and the input is applied at the non-inverting terminal of op amp, and this is also called as Howland current converter. Who is invented this voltage to the current converter with grounded load? That's why we are also calling it as Howland to current converter. So before calculating the load current IL, first of all we have to calculate the input voltage V1 for this non-inverting op amp. Once we calculate the value of V1, then we can easily calculate the load current IL from the expression of V1. So first I am going to calculate the value of V1. Apply KCL at node V1. What happened? If you apply the KCL, the current I1 is entering from this, that is from the input side, and the current I2 is entering from the output side. Both will be connected at node V1, and the current leaving from the load is IL. So I am considering IL will be equal to I1 plus I2. How can we get this IL is equal to I1 plus I2? Apply KCL at node V1. Okay, at node V1. So first calculate IL, calculate I1, and then calculate I2. Substitute all those values in this expression, then we can easily solve the output load current expression. So what is IL? IL is equal to V1 minus 0 divided by RL, which is nothing but according to the Ohm's law. Next, what is I1? So I1 is calculated in between these two nodes. Then what happened? Vi minus V1 divided by R. Next, what is I2? I2 is nothing but V0 minus V1 divided by R. So finally V1 divided by RL is equal to Vi minus V1 divided by R plus V0 minus V1 divided by R. Next, we can calculate the VO, which is nothing but output voltage V0 value. We can easily calculate the output voltage V0. So V1 divided by RL, we will be also called it as IL. So IL is equal to Vi minus V1 divided by R plus V0 minus V1 divided by R. So take LCM and we will be rewrite it as R into IL is equal to V0 plus Vi minus 2 into V1. From this, V0 is equal to 2 into V1 minus Vi. V0 is equal to 2 into V1 minus Vi plus R into IL. This is about V0. So from this we can easily calculate the value of V1 also. Once we calculate the value of V1, then we can rewrite the expression as V0 is equal to. Why? Because this is the non-inverting op amp. We calculated output voltage V0 is equal to 2 into V1 minus Vi plus R into IL. But our main intention is to calculate the value of V1. Once we calculated the value of V1, then we can easily calculate the gain value. So what about this output V1? So V1 will be rewrite as V0 plus Vi minus R into IL divided by 2, which is nothing but V1 value. And if you look at this circuit diagram, it will be looks like the non-inverting op-amp. So what can we write for the output voltage of the non-inverting op-amp is V0 is equal to 1 plus RF by R1 into V1. Yes or no? 1 plus RF by R1 into V1. Here RF is equal to R as well as R1 is equal to R. So we will get V0 is equal to 1 plus R by R into V1, which is nothing but 2 into V1. So V0 is equal to 2 into V1 means what? V0 plus Vi minus IL into R divided by 2. Okay. 2 will be cancelled. So V0 is equal to we calculated V0 is equal to V0 plus Vi minus IL into R. So V0 minus V0 is equal to 0, which is nothing but V0 minus V0 is equal to Vi minus IL into R. From this we calculated Vi minus IL into R is equal to 0. So what about IL? IL is equal to Vi divided by R. So from this what we calculated is the output load current is directly proportional to the input voltage. So from this we concluded that this is nothing but the voltage to current converter, that is output load current is proportional to input voltage. So with the help of Howland current converter also we can calculate the load current. Okay, that's it for the voltage to current converter. Till now we discussed about voltage to current converters. There we have seen two types of voltage to current converters. They are depending upon the connection of the load, they are divided into two types. One is floating type and the other one is grounded type. Now I am going to discuss about applications of V to I converter. There are several applications are there for the V to I converter. In this I am going to explain some of the application. Coming to the first application, the V to I converter will be used as a low voltage DC voltmeter. In this case I am considering the floating type V to I converter. Yes or no? Why? Because this is the floating type V to I converter. So here I am replacing the load resistance with the help of D-Arsenal meter, and for the removing of the errors in the op-amp we are going to be used the offset compensation network. Here I am using this offset compensation network to remove the offset errors present in the op-amps. Now I want to calculate the low voltages. So what I am going to do is, if the switch first before calculating the calculating the voltage, first we have to know about the equivalent Thevenin's value. For this is 10 ohms. The effective equivalent Thevenin's value for this compensation network is 10 ohms. Now what happened is, when the switch position is at 1, then the resistance R1 will be equal to 1 kilo ohm plus 10 ohms, and 10 ohms is very less when compared with 1 kilo ohm. Then we will get the R1 is 1 ohm, and we all know that I0 is equal to V in divided by R1. Yes or no? And while you are choosing the Arsenal meter, take care. Why? Because that Arsenal meter doesn't shows any effect in the feedback path. Then only you can calculate the accurate readings. So take care while choosing the D Arsenal meter. And I naught is equal to V in divided by R1. Suppose if the output current is 1 milliampere, so 1 into 10 to the power of minus 3 will be equal to Vi divided by R1. So for 1 milliampere, if you are applying the resistance we already calculated, which is nothing but 1 kilo ohm, I am assuming the input voltage is 1 volt, then obviously we will get I naught is equal to 1 milliampere. So for the full scale deflection of the current, suppose if the full scale deflection of the current is 1 milliampere, for that we require 1 volt of the input voltage if you connect the switch position is at 1. Suppose if you connect the switch position is at 2, okay, then what happened? So then R will becomes equal to 5 kilo ohms plus 10 ohms. Then we will get 5 kilo ohms. So we all know that I naught is equal to Vi divided by R1. So we are assuming the full scale deflection of the meter is 1 milliohm. So 1 into 10 to the power of minus 3, 5. R1 value will be 5. So V1 will be chosen as 5 volts. Then only we will get the full scale deflection as 1 milliampere if your input voltage is 5 volts. Similarly, if you want to increase the range of your voltmeter, then what you are going to do is you are going to connect the switch positions for switch number 3 and switch number 4. So we will get the voltage is increase. We will get the increased voltage ranges. Now what I want to tell you is in the applications of V to I converter, so output current is always depends upon the input voltage. For an example, if you are assuming the full scale deflection in the D Arsenal meter is 1 milliamperes, then depending upon the switch positions, the input voltage will be varying. Okay, the input voltage will be varying, and while you are take care while you are choosing the input values. Why? Because here the supply voltage range is for plus 15 volts to minus 15 volts range only. So while you are choosing the input voltages, you should not cross the input voltages are plus or minus 13 volts. Then only you will get the accurate input values for the 1 milliampere full scale deflection. That's it for the low voltage DC voltmeter. Next we are moving on to the AC voltmeter. Coming to the low voltage AC voltmeter. Low voltage AC voltmeter. Previously we discussed about low voltage DC voltmeter. Now in this case we are going to see the low voltage AC voltmeter. Here we are going to be used the full wave bridge along with the D Arsenal meter will be connected in feedback path to the op amp. Here also we are treating it as a floating type V to I converter. So in this case the alternating current I naught will be converted to DC. So in case of positive input voltage, what happened is the diodes, this is the I naught current direction, the alternating current I naught. When the Vin is positive voltage, then the diodes D3 and D4 will be conducting, and when Vin is negative, the alternating current I naught passing through D2 as well as D1. So the diodes D1 and D2 are conducting. So in both the cases, that means the input voltage is positive or the input voltage is negative, the direction of the current passing through the arsenal meter is same. While in case of the positive current, the direction of the current is from positive to the negative. While in case of the negative current, the direction of the current is from the negative to the positive. That's why what I am telling is the direction of the current in the arsenal meter is same for both the input waveforms. That means for the positive waveform as well as for the negative waveform. So the average of the current passing through that D arsenal meter will be gives the DC value. Whatever the average current which is passing through the arsenal meter is gives the DC value. That we are going to be measured while using the low voltage AC voltmeter. Okay, not only that, if you want to increase the range of voltages, then like previously what we have seen in the switch positions, just arrange the switch positions from 1 to 2 to 3, 3 to 4, then automatically the range of the input voltages are increases. And one more thing you have to remember is, if you want to calculate the RMS voltages by using the D arsenal meter, if you want to calibrate the RMS values while using this D arsenal meter, then you have to include a factor 1.1 for the calculation of RMS values for the input sinusoidal signals. That's it for the low voltage AC voltmeter. By using this circuit, we can calculate the voltage. So alternating current I naught will be converted to voltage in this case. So we calculated the AC voltages. Listen, if you compare the low voltage DC voltmeter with the low voltage AC voltmeter, in case of feedback path, there we are having only the D arsenal meter, but whereas in case of low voltage AC voltmeter, in the feedback path along with D arsenal meter, we are also chosen the full wave bridge. That's it for the low voltage AC voltmeter, and we are also see some more applications for the voltage to the current converter. V to I converter will be also used as a diode tester and match finder. How can you use it as a diode tester and match finder is, you just replace the load resistance with the diode. So then we can use it as a diode tester and match finder. Initially we have to nullify the errors which are present in the op amp with the help of offset null circuit, and the output current is set with the help of input voltage and resistance, which is nothing but I naught is equal to V in divided by R1, as long as input voltage and the resistances are constant. So obviously the output current is also constant. So if you want to see the values of the diode across the values of the diode, what you have to do is, with the help of voltmeter you can calculate the voltage across the diode. Once we know the value of the diode, then we can easily judge the performance of that diode. Replace the diode and you can use some other diodes also. We can easily calculate the diodes test. We can easily calculate the match finders as well as diode tester. Mainly the output voltage will be calculated as V0 is equal to V in plus Vd. So we have, our main intention is finding the or testing the diodes, and which type of diode we are going to be used, that we will be calculated with the help of voltmeter. So find out the voltage across the diode, then with that value we can easily calculate the performance of the diode. Not only this diode tester and match finder, we can see the other application of the V to I converter also, which is nothing but Zener diode tester. Just now only we have seen it that the V to I converter is used as a diode tester and matched finder. Okay, now we are replacing that diode with the help of Zener diode. So you can use it as a V to I converter is also used as a Zener diode tester. Here the Zener diode is connected in a reverse biased condition in the feedback path. So first what we have to do is set the output current. Output current V0 is equal to Vin divided by R1. So to remove the errors, first before calculating before setting the output current by using the offset null circuit, we are going to remove the errors in the circuit. So while setting this input current, it is always greater than the knee current of the Zener, then only the Zener is rated, otherwise the Zener will not be rated. Once the Zener is rated, then we can easily calculate the value of Vz across the Zener diode. So while setting the output current I0, take care the values of Vin and R1. Those the I0 value should be greater than the knee current of the Zener, otherwise the Zener will not be rated. Okay, like this we can calculate the Zener diode tester. So all these are the applications of V to I converter. Just now only we discussed the V to I converters are used as a low voltage DC voltmeters as well as low voltage AC voltmeters, and next one is diode tester and matched finder. Last one is Zener diode tester also.